Hello and welcome, Algebra 3-4 classes for Mr. Robinson. This is the Chapter 2 video study guide with me. I will give you some example problems, and they'll be straight out of the Chapter 2 practice test that you took. Okay, now this is my first video with you guys. It will be pretty long because I'm going to have some notes alongside these problems as well. Good explanations on both. Please skip around as you need to. I'll put a time frame where each problem is laid out so it can help you out. You're going to see this a whole lot. This happens every single time I run a video. Just ignore it. So what's going to happen here is I'm going to do some notes based on the beginning of what we did, domain range relations functions. And then I'm going to do the problems that are associated with it. So the problems might go a little bit out of sequence. So just bear with me on that. Find the problem that you're associating with it, and you'll be good to go. Okay, first I'm going to give you some definitions here, and they're a little formal, and we'll go over them and see if they make sense as we do the problems too. Okay, a relation first to start off. This is a set of x and y coordinate pairs that can be plotted on a graph. This includes lines and curves. So what is a relation exactly? Well, let me give you a set. It starts with these curly braces here. Let's give some points. 2, 1, -3, 7, 0, 4, etc. Here are 3 points. If I plot them on a graph, they all work together in their own system. That's what the curly braces mean. So that's a relation. Straight up, nothing else to it. Here's another relation. Y equals 4x minus 7. The fact that we know this as a line does not negate the fact that there are x values and y values that associate with one another. Like if I plug in 1 for x, I get -3 for y. That is one of the points of the infinite amount of points that I can use for x and y in this relation. So a line is still a set of points or xy coordinate pairs. Okay, domain and range. Domain is the set of inputs in a relation. So basically all of your x values. In this example here, I have 2, -3, and 0. Here's my domain. 2, -3, 0, or you can put that in proper order, -3, 0, and 2. It's just the values that work for your relation. In this case, a domain, which we'll go over some problems like it, it's what values for x can I plug in? Because as I told you, I said I can choose an infinite number of x values and y values, and I can choose it from negative infinity to positive infinity. So I can go on forever. So in this case, my domain is all real numbers, if you remember that symbol. Basically, do I have a restriction on what can I plug in for x to be able to get a value out for y? And the answer is no. I can plug in any number, I'll still get an answer. We will have examples where that is not true. Okay, the range is the set of outputs, or the y values in a relation. So in this case, I'm looking at the y's. I'm looking at 1, 7, and 4. For that function, or excuse me, for that relation right there. So my range would be 1, 7, and 4. We've done mapping diagrams as well. I'm not going to talk about that per se, but you can map whatever number was to the other one as well. You can draw them vertically. So the range works the same way. I plug in values for x here. What values do I get out for y? Or are there restrictions on what y will be? Not really so much with linear functions. It all depends. You can have a slope of 0, all that. But for y, this can be any real number. I plug in some value for x, I'll get some value for y. I plug in another value for x, I'll get another value for y. And it continually will go like this as your graph, which means it can go further up or down, all the way down to negative infinity up to positive infinity. Okay, a function is a relation. So it is a relation, which means it's a set of x and y coordinate pairs, blah, 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 blah. Where? So here's the specific thing. Every element in the domain is paired with exactly one element in the range. No more, no less. All that means is, you look at it, you look at these two right here. I will draw a mapping diagram for you. I draw a column for my domain and a column for my range. And I draw out these points, 2, -3, 0, and 1, 7, 4. The fact of the matter is, I can map the 2 to the 1 because 2, 1 was one of my coordinate pairs. 2, 1. Then -3, 7, and 0, 4. Only one x value that stems off to 2 different y values. Okay, and that's an important thing to understand. If I have a fourth point. Let's call it 2, 3. That means in my mapping diagram, there is a 2 right there, and I can write a 3 right here as well. Now, suddenly, 2 goes to 1 and a 3. This is not good as far as functions are concerned. They say, I can't have 2 points on top of each other. Here's 2, 1. Here's 2, 3. Suddenly 2 points are on top of each other. So you remember the vertical line test. This fails the vertical line test. So this is not a function. Functions are only where I can only have one y for every x. Or if you look at an equation like this one right here, y equals 4x minus 7, I plug in values for x here. I cannot get multiple values for y. If I plug in 1 for x, I'm going to get negative 3 for y. I can't get a different number. I plug in 2 for x, I'll get 1 for y. I plug in 3 for x, etc. So it keeps going, and you don't get multiple values for any one x that you plug in. However, it is okay to have multiple x's for any one y, although that does not happen in linear functions, linear equations. Okay, let's do some of these examples. I'll do number 1 first to start. Now, the other thing about functions really is you plug in a value for x, you get one for y. We talked about that. Here's a notation called function of x, f of x. That is not f times x. It's function of x, and basically all that means is, first of all, you're looking at a function, and second of all, whatever number is represented here, you substitute for x, and you figure out what value that is for y. So pretty simple. F of negative 12 here, I'm going to plug in negative 12 for x. You get 5 over negative 12 plus 2, which is 5 over negative 10, which is negative 1/2. So the f of negative 12 is negative 1/2. Another way of putting that is there is a value, there's a coordinate pair on this graph that is 12, comma, negative 1/2. Here was the x value, and here's the y value associated with it. Remember, there's only one y value we'll have. Okay, this one's a little different. We got 12 f of 8. This means 12 times the f of 8. So what I'm going to do is I'm going to take the f of 8 first, then I'll multiply it by 12. Okay, so the f of 8 is 5 over 8 plus 2, which is 5 over 10, which means f of 8 is 1/2. So if f of 8 is 1/2, 12 times the f of 8 is 12 times 1/2, or 1/2 of 12, which is 6. So again, another coordinate point that you have here is 8, comma 6. These are coordinate pairs within your function. This particular, well, I guess this is different because it's 12 times it. Okay, g of negative 3. Suddenly, you know, this is still a function. It's not a gunction. It's still a function, just using a different letter, so that way you can have multiple different functions. G of x, plug in negative 3 here. The only thing I caution you of is order of operations. Make sure that you know that when I do 3 times negative 3 squared, I will do negative 3 squared before I do 3 times negative 3. And same thing here. Keep note of your negative. So negative 3 squared is 9. 9 times 3 is 27. So this is 27 plus 15. A negative times a negative is a positive. If you didn't know that, please watch the movie Stand and Deliver. Okay, so let's see here. 42 plus 6 will give you 48. So g of negative 3 is 48. Again, that means there's a coordinate point, negative 3, comma, 48. F of negative 1 plus g of 1. So take the f of negative 1, add it to g of 1. And I'm kind of running out of space here. Let me shift these over. The benefit to these videos are if I ever delete something, you can go ahead and rewind and check it out again. So f of negative 1 is 5 over negative 1 plus 2, which is 5 over 1, which is 5. G, I'll use a different color. G of 1 is 3 times 1 squared minus 5 times 1 plus 6. So that is 1 squared times 3, which is 3, minus 5 plus 6. And that will give me negative 2 plus 4. So I can do 5 plus 4, so my final answer will be 9. Okay, that's f of negative 1 plus g of 1, that gives you 9. Okay, now I want to talk about domain a little bit. Now, I won't give you range when it comes to equations, but I will give you domain. And what that means is you can ask domain in two different ways. Either what can x be, or what can't x be. Those are the only things that you ask, and they basically answer the same question. Whatever x can't be, if you write that mathematically, that means that x can be anything but what you put. Or what can x be, that means there are restrictions on what x can't be. Okay, as far as you're concerned, there are only two scenarios, really, where we need to consider that x is going to have restrictions. And that is in denominators that are 0. I can't write, though. Denominators of 0. And negative numbers in square roots. Okay. If I have a negative square root, or if I have a denominator of 0, that means there are issues with what x cannot be. So let's go and take a look at that. Number 5, and notice how I jumped ahead. I skipped 2, 3, and 4. We'll do that later. Number 5 here says g of x equals 1 over 4 plus x, the quantity 4 plus x. So what I'm seeing here is x is in the denominator, so that means there might be values of x that I choose that will make this thing 0, and that's a problem. I cannot let 4 plus x equal 0. So I'm going to write an equation down here before I get going. 4 plus x cannot equal 0. If that's the case, treat this like an equal sign in that you want to balance the equation, quote-unquote, solve for x. I'm going to subtract 4 from both sides. X cannot equal negative 4. And that is actually my domain. So when we ask about what can or can't x be, x cannot be negative 4. X can be any number but negative 4. If I have negative 5, that's fine. I can have a negative in the denominator, but I can't have negative 4 because that'll make my denominator 0. And that is a problem. We're not looking for 0 denominators. Zeros in denominator. Okay, you have one right here, y equals negative x squared plus 12. And although we haven't worked on quadratics yet, you've seen parabolas before. I want you to think about parabolas for a second. This one will be a downward-looking parabola, and it has arrows like that. Okay, there's a restriction on range. There's some place where y can't be up here. Y can be down there. But x's, I can go left and right as far as I want. That's the visual look. The mathematical look is plug in a number for x. Can we square that number? Absolutely. It doesn't matter what the number is. It can be negative 10 billion. That's a B with billion for all I care. You still get a value out for y. So in this case, your solution is all real numbers. That's your domain. X can be, you can plug in any number for x and you are going to get a value out for y. It might be extremely big, might be extremely small, might be extremely insignificant, might be close to 0, but you will get a value out for y. Guaranteed. Because our only restrictions are denominators of 0 and negatives and roots. And we're about to see a negative and a root here. Okay. This is, well, actually, we're going to see denominator of 0 as well. So here's a tricky one. 1 over the square root of x minus 5. So I'm going to take a look inside the square root first. I'm going to say x minus 5 cannot be a negative number. Because if x minus 5 was a negative number, then I take the square root of a negative, and that's an issue. Remember, I'm currently ignoring this denominator thing right now. I just want to look at negative first. We'll talk about the other one after. So, if x minus 5 can't be negative, that means that x minus 5 must be 0 or positive. So here's the mathematical expression for that. X minus 5 must be greater than or equal to 0. That's a way of saying what x can be. It can be positive or 0, and that's why I'm saying what x can't be. Saying it can't be less than 0, can't be negative. Add 5 to both sides, x is greater than or equal to 5. So that is a domain that we are currently looking at right now. That is the biggest of possible restrictions that we'll have. But we're not done, because you write x is greater than or equal to 5 here, you might run into an issue, because you have to keep in mind here that x is in the denominator. So now we're saying, uh-oh, this whole thing better not be 0. We better not get the square root of x minus 5 to be 0. And we know that the square root of 0 is 0. So x minus 5 better not be equal to 0. If that's the case, x better not be 5. So here's a combination of two kind of domains that we're looking at here. Now we have to combine them. Here we said, all right, as far as the square root thing, x must be greater than or equal to 5. Here, as far as the 0 thing, x must not equal 5. So basically, x can be anything but 5 or less than. So we're going to cross out that greater than or equal to. We're just going to change it to greater than. X must be greater than 5. Because remember, if x was 5, that would give us a 0 as the denominator. That's an issue. We can't have that. Okay, the last one, we're going to do the same thing, but now we have multiple x's here. All right, let me delete this actually. You've seen it. That's gone now. Okay, f of x equals the square root of x over x minus 9. Let's treat these separately now to start, and we'll see if anything coincides or collides or anything. We look at the top part. We say, all right, x is the only thing inside the root, so x itself better not be negative, because if the square root's negative, then we have an issue. So here we say x is greater than or equal to 0. That's something as a part of our domain. It better be 0 or positive for this. Now we look at the denominator and we say, okay, x minus 9 can't be 0. I'm sorry, not 0. Yeah, x minus 9 can't be 0, so we're going to have to pay close attention to that. Because if x minus 9 was 0, we would get 0 in the denominator, and that's an issue. So x cannot equal 9 once you do that math. So now we're taking a look at these two guys right here in our domain. And this is kind of the way you just got to put this right here. You're going to say x better be greater than or equal to 0 for this part to work, and x better be not 9 for this to work. So x is going to be everything greater than or equal to 0, but x can't equal 9. That's kind of the best way I can put that one for you, because it'll basically jump 9 and do anything else that it wants to, and you'll still get a number out for f of x. Okay, I'm going to move on there, and I'm going to go to slope. Again, if you have any questions, just please ask as you go. You just take a look at it, rewind, all that stuff. Slope, okay, definition I'm writing here is the rate of ascent or descent of a line. For slope, we refer to lines, not curves. The steeper the slope, the larger the absolute values associated with it. All I mean by that is if you have a slope of like 10, that means it's steeper than something with a slope of 2. And even a slope of negative 10 is steeper than a slope of negative 2, is absolute value, even though it's going the other way. But I'm just saying that the value itself makes it a steeper look, whether it's going upward or downward. Okay, what does all this stuff mean? Slope, I want to define as my rise over my run, or the change in y over the change in x. Delta refers to change, that triangle there. The way we put that here is this formula, y2 minus y1 over x2 minus x1. All that means is you have 2 points there, x1, y1, and x2, y2. You're trying to say, how much do I climb, the difference in my y values, and how much do I run, the difference in my x values? So subtract x2 from x1, y2 from y1, and you divide your y's from your x's. And that gives you your slope. So we'll do examples of that. Positive slope represents a graph going that way, upward, or downward to the left. And a negative slope is downward when you go to the right. Okay, here are 2 ones that involve slope. Take a look at these. And I want you to say, all right, let's see here. Find the value k, so the line kx plus 7y equals 6 has m equals negative 5. Now, m is your slope. We saw that on the previous screen. M refers to slope. I should have put that up here, m. All right. So what we want to do here now is say, all right, we need to write this in a form where we know where we can find our slope. This is standard form, something I'm about to talk about next. But in standard form, it doesn't reveal slope. Just because there's something in front of the x does not mean that k is my slope. So I need to transform this into something like, let's say, slope-intercept form. Because slope-intercept form reveals the slope to you. So I know I'm kind of jumping ahead here doing this problem without doing slope-intercept form first, but I think you can still figure it out. Slope-intercept form, solve for y. So I'm going to subtract kx, and I get 7y equals negative kx plus 6. Divide both sides by 7, I get y equals negative k over 7x plus 6 over 7. I'm not asking you to graph this, but what they're going to say here is we know slope-intercept form is y equals mx plus b. And if we use y equals mx plus b, that means that our m here is that value that's in front of x when we're in slope-intercept form. So as far as we understand it, our m is negative k over 7. Okay. The other thing we know about m is that it's also negative 5. So if m is negative 5, that means negative 5 equals negative k over 7. So what value for k makes this true? Well, you can multiply both sides by 7 and all that, or just say this number over 7 equals negative 5, this has to be 35. 7 times negative 5 is positive, or is negative 35. So negative 35 equals negative k. K equals 35. That's the value you plug in for k to make that true. And so in this equation, that's what that equation would then look like. This is an equation in standard form. The equation in slope-intercept form would be negative 35 over 7x plus 6 over 7. Not that we're graphing it, but you know. Okay, the next problem I'm going to do, solve for y if the slope between the points 8 comma y and negative 2 comma negative 4 is 5. So I want you to look back at this equation here, and what we said here was we have an xy pair and another xy pair. We take the difference of our y's, divide it by the difference of our x's. That's where we get our slope value. Now in this case, they give us the slope value. So in this m equals y2 minus y1 over x2 minus x1, they give us m, which is 5. So 5 equals, check this out, we can call this y2 negative 4 minus this y value. I don't know what that y value is yet. We got to figure it out. Over negative 2 minus 8. Okay, so 5 equals negative 4 minus y over negative 10. Multiply both sides by negative 10, we'll get negative 4 minus y equals negative 50. Add 4, negative y is negative 46, so y equals 46. Okay, so it's a strange number. You look at this and you're like, 8 comma 46, that seems a little high and excessive. Just make sure that you look at what you're doing. You make sure. I went from negative 2 to 8. That's 10 spots right there. So yeah, you went 50 more than negative 4. So that's all you were doing on that one. Okay, let's go to our equations. Now, I had one of your students here take a picture of this, so thank you so much. This was what's on the whiteboard, and you actually can't use this for the test, just to be fair with all the other classes, because they won't necessarily use that. Here are different forms that we're going to be looking at for now. I'll ignore vertex form for now. That's vertex form of absolute value. We're looking at standard form, point slope form, slope-intercept form, and hopefully you've done them enough so that they actually are just very, very easy to remember at this point. Right? I'm not expecting you to forget them. I'm also not expecting you to memorize them. I'm expecting that you've known them enough that you've done them. But let's talk about them for a second. Standard form comes in this form, ax plus by equals c. A, b, and c are all integers. Think of them as whole numbers. You want your a value to be positive. So if they're asking for you to solve something in standard form, which is highly unlikely for your test, manipulate everything so your x and y terms are on the left side of the equation. You have a constant on the right. And multiply by a common multiple so that you've gotten rid of all your fractions. Okay, so that's the idea there. It's very the next one's point slope form I'll talk about, and this can be gotten from your slope formula. Multiply both sides by x2 minus x1, you kind of get this equation. Point slope form gives you your slope m and an xy pair, y1 and x1 right there. Okay, x1, y1 is a known point that you have, and it's good to do this if you are working with 2 points that are given and you have to put it in a form. And you can easily, from either of these, solve for y. If you solve for this y, or if you solve for this y right here, you can get slope-intercept form, which is my personal favorite, and it's the one that's used in the masses for a lot of different problem types, including the linear model problems we're going to do. M is the slope and b is the y-intercept. Again, I'll do some problems with these and see if they all make sense as we go along. Again, I'll do vertex form later. Okay, write an equation for the line passing through 2, negative 8, and negative 4, 7 in point slope form. Point slope form looks like so. Y minus y1 equals m times x minus x1. Now, in order to do this, that means we need an m. I have 2 sets of x1, y1s that I can use, one or the other. Doesn't matter. But I need to find an m. And to find an m, I need to find the change. How much did I rise from negative 8 to 7? How much did I run from 2 to negative 4? That'll be my slope. So m is y2 minus y1 over x2 minus x1, which is 15 over negative 6, and that can be reduced to negative 5 over 2. So my slope is negative 5 over 2 right there. And pretty much done at this point. All I need to do is insert here. That's my m. And I can choose, I'm going to do both solutions for you, and then I'll drag them over. Here's an example of one solution. I can make y minus negative 8, which is y plus 8, equals negative 5 halves, times x minus 2. That's one set of points. The other set of points I could choose is a negative 4 and 7, so I'll get y minus 7 equals negative 5 halves times x minus negative 4, which is x plus 4. These equations look different? Well, heck, they do look different, don't they? But they are the same equation. Because if I transformed either of these, or both of these, into slope-intercept form, you'd get the same exact y equals mx plus b. Now, I'm not going to do that for this problem. I'll do it for this problem right here. But that's the idea behind those, and there you go. Hopefully you're following along with the answer key, and hopefully these are coming right, because I'm not double-checking them. It's probably a bad practice. Okay, write an equation. This is number 3. Write an equation for the line passing through negative 9, 7, and parallel to the line 5x plus 3y equals 8 in slope-intercept form. Okay, so you have a lot of different things that you have to do here. You have to make sure that you write an equation, a line passing through negative 9, 7, and parallel to this line in slope-intercept form. Okay, parallel means same slope. I have another line that has the same slope as this line, and obviously a different y-intercept. Otherwise, it's the same line. So I'm going to take 5x plus 3y equals 8, and I'm going to say, all right, this is in standard form right now. I can't use standard form and see the slope with it, so I might as well put this in slope-intercept form. Let's do it. Subtract 5x, divide by 3, I get y equals negative 5 thirds x plus 8 thirds. Now this is the equation for this line, right here. That is not the equation for the line passing through negative 9, 7 and parallel to it. So what I'm going to do is say, all right, I know that my slope is negative 5 thirds for my new line. I know this because I know it's parallel to it. So my new line will come, because they're asking me to do in slope-intercept form, I'll just go ahead and write this in slope-intercept form. Y equals mx plus b. Now you'll notice that I wrote b literally because I don't know what my y-intercept is for this equation. So I have to find it out. And how do I find it out? Well, I have to choose a known point that I have. In this case, negative 9, 7. I know that this thing passes through negative 9, 7, so I know if I plug in negative 9 for x and 7 for y, that'll be a solution to this guy right here. It should be a negative 9 plus b. And I solve for that b, and when I do, I'll rewrite this equation as such. So 7 equals, all right, I got negative 9 divided by 3. That's negative 3. Negative 3 times negative 5 is positive 15. So that's 15 plus b, and b equals negative 8 when you subtract 15. Okay, so my final equation is y equals negative 5 thirds x minus 8. Again, this is the line that's parallel to this original line. Maybe it doesn't look like it, but if you compare it to this one, y equals negative 5 thirds x plus 8 thirds, same slope, different y-intercept. So they will never, ever intersect with each other, and they have different places that they cross through. This one passes through the point negative 9, 7. Okay, final one. Ooh, standard form. Here we go. Write an equation containing 5, negative 2, and perpendicular to the line 3x plus 4y equals 5 in standard form. This one actually requires a lot of work. I'll explain why. First of all, perpendicular means opposite reciprocal slope. We've talked about that a few times there. And all that means is whatever slope you have, flip the values, like negative 5 thirds, and change the sign. So the opposite reciprocal of negative 5 thirds is 3/5. That's an example. So in order to do that, I need to find the slope of this line. Now this is in standard form, just like this one. That's not the only problem. The other problem is I have to put it back in standard form in the end. So this one, when I finish solving for it, okay, I got this thing, but this is slope-intercept form. So we're going to have to do a little more work, which means I might need a little more room. So we'll see how we do here. All right. 3x plus 4y equals 5. Let's put this in slope-intercept form first. Y equals negative 3/4 x plus 5 over 4. And again, this whole y-intercept fraction thing, it's no biggie. Because what I'm going to do is say, I don't need that y-intercept. We're going to find a different one anyway. All right, the slope of this guy right here is negative 3/4. So a parallel line would have a slope of negative 3/4. I'm not looking for that. I'm looking for the one perpendicular to it. This symbol means perpendicular sign. And 4/3 is its opposite reciprocal. Okay, so from this point, what we're going to do is Plug this back in, like y equals 4/3 x plus b. Same idea. We need to find out what this b is based on what point it passes through. 5, -2. So we'll do the same thing as we did last time. Only difference is we'll need more steps because we need to put this back in standard form. So I'm going to do 5 for x, -2 for y. Looks like we'll have some fraction issues too, which is always my favorite, of course. Okay, 5 times 4 is 20/3. So -2 equals 20/3 plus b. I have to subtract both sides by 20/3. So I'll do -2 minus 20/3 equals b. This is kind of an unfortunate one, not having fun with it. -2 I need to write as a fraction that's divided by 3. So -6/3 will do. Finding a common denominator, that's all I'm doing. Okay, -6/3 minus 20/3 is -26/3. So there's my b value. So now the equation I'm looking at is going to be y equals 4/3 x minus 26/3. Now this is not my final answer, but I am in good shape here. The last part I need to do, based on what I was talking about before, in standard form, get x over here, and get all these as integers, and make sure your a is positive. So let's check that out. Y equals 4/3 x minus 26/3. Right now my x is on the right side of the equation. I got to subtract 4/3 x over here. So I'll get y, or -4/3 x plus y equals -26/3. Okay, I have fractions. Here's the tricky part for some. I can actually change these numbers as long as I keep my equation balanced. So I'm going to multiply both sides by a number so I'll no longer have fractions. -4 is over 3, y is over 1, and -26 is over 3. If I multiply both sides by 3, this will cancel out my fractions. I'll have 3 times -4/3 x plus 3 times y. That equals 3 times -26/3. So you'll notice how these 3's cancel here. 3/3, let me choose a different color. 3/3 and 3/3. So now I'm left with -4x plus 3y equals -26. Nearly done. So the last thing I need to do here, though, is make this x term positive. So you can say multiply both sides by -1. I just say switch all these signs. Get positive 4x minus 3y equals positive 26. And that was a long problem. In your answer key, I think it says 4x minus 3y minus 26 equals 0. Same thing. I use standard form this way. You'll see it in a book this way. I wouldn't hark you for doing this. Just to me, this one looks cleaner. And there's a benefit to doing this one graphing. We'll talk about that later. Okay, let's talk about direct variation. This is really much easier than we make it out to be. Now, I don't make it out to be that easy either. You can tell I wrote a lot. Okay, but it really is very simple. I don't want to confuse you with it, but let's go through the reading. It's a proportionality, meaning that you can set up proportions with this guy between the independent x and dependent variables with a constant ratio. It's all jibber jabber. You don't have to define that on your test, but you have this equation here, y equals kx. It's like y equals mx plus b, only your m turned into a k for some reason, and your b is 0. It's the same thing. So it's slope-intercept form without the y-intercept. So it really is an easier version, to me. It's an easier version of slope-intercept form, and you're going to see the sentence a lot. Y varies directly with x, or you'll see direct variation, or directly proportional, or anything of that nature. It's very important that you find that in the problem, though, because then you know if your y-intercept is 0, then a point in your graph is 0, 0. It crosses through the origin. And that's the whole thing about proportionality. These things grow at the same rate. Here's the translation. Literally, all that stuff. Y varies directly with x. All that means is the growth of y is directly affected by the growth of x. Directly affected. If x does not grow or does not exist, neither does y. So if x is 0, then y is 0. There's always going to be this point in direct variation. Plug in 0 for x, you get 0 for y. K represents the constant of variation, the rate at which y grows by based on x. So the whole idea behind that is it really is your slope, but we talk about rates in word problems. An example, this isn't the problem I'm going to do, but an example that we've seen before is driving a car, how many miles you travel, and paying for gas, how many dollars you spend per mile driven. So your K is dollars per mile. That's the rate, the constant of variation, how much you vary by. If you do not drive the car, in this case, if X is 0, if you don't travel any miles, you will not spend any gas money. Y equals 0, $0 spent. However, your pay will base entirely on how many miles you drive. So let's say, for instance, you pay 50 cents per mile. I think that's way too expensive, but I don't care. 50 cents is $1.50, or is $1.50? It's 0.50 like that. So Y equals, I'll just put 0.5x. There's a rate right there, right? It kind of makes sense. So all that means is if you drive 10 miles, how much money do you pay? Well, you pay 50 cents times 10 miles. That equals $5. So that's the whole rate idea. So let's do some problems with that. Okay, Y varies directly with X. This is huge. You need this sentence. You need something that tells you about direct variation. If X equals 8 when Y equals 4, they want you to write an equation on that. And so what we're going to do is this. We can look at this multiple ways. I'll just look at it this way. You know the equation is Y equals K times X. So we have to figure out what K is. Pretty simple. We have a solution right here. 8 comma negative 4. Plug in negative 4 for Y and 8 for X. I think this is simpler than slope-intercept form because now you don't have to add anything to it. It's one less step, but sometimes when that thing's a fraction, shoot, that becomes trouble. Divide by 8, you get K equals negative 1/2. So your equation for this direct variation is Y equals negative 1/2 X, meaning now we can start plugging in values for X and get values for Y. Or plug in values for Y and get values for X. Doesn't matter. This isn't a word problem, but we can make sense of word problems when we do this. Okay, part B, find Y when X equals 6. Simple enough. Substitution. We did this in the very beginning. So Y is negative 3. Another way of putting that is a point on your graph is 6 comma negative 3. Just like you have 8, negative 4. And just like you have 0, 0. So these are different points on your graph. They're all with the same slope of negative 1/2. And find X when Y equals 22. Same idea. Plug in 22 for Y. Okay, hopefully you know how to divide by negative 1/2 or multiply both sides by negative 2. Cancels. You get X equals negative 44. So there's another point on your graph. Negative 44 comma 22. Okay, so that direct variation thing, it's super important as far as understanding what it means. If I have a graph, okay, it's this line. I mean, we've done this line plenty of times. Here's my slope. Negative 1/2. Here's my slope. It crosses through the origin, and it goes down 1 over 2, down 1 over 2, down 1 over 2. And these points exist on that graph. That should make sense. Your X value is twice the amount of Y, and it's the negative version of it. So that makes sense there. I'll move on, though. Okay, linear models. Here's where we'll do some word problems, and hopefully we run into a direct variation problem along the way. Linear models are word problems that require a mathematical setup. In this case, we're going to use Y equals mx plus b. Some important things here. M refers to a rate, something that grows over time. It's some, miles per hour, dollars per mile we did. It doesn't matter. Students per classroom, all these different things. B is a fixed amount, and it's like a startup amount. So you saw in direct variation, there was no startup fixed amount. It started at 0. So I did the car thing. I want to give an example here. If we did this one, same thing. Miles traveled was your slope, and all that stuff. Or I'm sorry, was your X, and your Y was how much you paid. What if you did a car rental place? Meaning you paid up front. You pay $50 to start off, like that. All that means is no matter how much I drive, I'm paying 50, plus however many miles I travel. We do the same thing for taxi word problems, as you've seen. We've done all of those. So we're going to set up a problem where B is that fixed amount, meaning no matter what X does, you will at least have B. So your goal when you do these problems is to determine what M is and determine what B is. Find M and B, and then you can start doing word problems. Oh, what if you drive 10 miles? All that stuff. we always have to consider the unit of measurement, always, 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 because these units have to be consistent. Whatever y is, let's say it's in dollars, m times x has to be in dollars, and b has to be in dollars. And just a little footnote, because you're doing dollars plus dollars, b and y will always be the same unit of measurement. If they set up a problem and they give you a fixed amount in like pounds, y is also something in pounds. And that's going to be important when you define your variables and when they give you more problems along the way. M times x is kind of interesting. That's where you have to apply a rate with a certain amount and certain units cancel. Maybe we run into that as we do a problem here. Okay, your new puppy. Oh. Your new puppy was born weighing 2.3 pounds. Born meaning your age was 0 years old. And at 0 years old, you have a fixed amount here. This is fixed at 2.3 pounds, meaning no matter how many pounds your puppy gains, she starts at 2.3 and you just add on from there. Okay, so in this case, if that's fixed, that means this is your B. So you know that B equals 2.3 already. You start from 2.3 and you add from there. She began growing and gained 1.2 pounds per week. Oh my goodness, you's getting fat, you little puppy. 1.2 pounds per week. This per is an indication of a rate, like miles per hour, all that stuff. A rate references m, so you know that m is 1.2. And again, this is a rate. This is pounds per week. So the important things here, this was 2.3 pounds, by the way, for B. If B is 2.3 pounds, then Y is also going to represent pounds. So I'm going to write an equation here. It's going to be in Y equals mx plus B form. And when I do this, I need to make sure that I understand my rates here. Y has to be in pounds. M times X has to end up being pounds. B has to end up being pounds. M is pounds per week. So in order to get pounds, I have to multiply pounds per week by number of weeks. So if you start at 2.3 pounds and you go 1.2 pounds per week, I say, oh, after 10 weeks, how many pounds did she gain? That's when you do that multiplication. You do that in your head. This is the on-paper setup. So what happens here is weeks cancel out, as we know how fractions work. So pounds equals pounds plus pounds. That makes sense. So looking at this, we know that X will have to be in weeks and Y will have to be in pounds. So Y represents, here, let me do X first, actually. So X represents number, or time, let's do time passed. This will be in weeks. Y represents the weight, total weight, puppy's weight. The unit used is pounds. Okay, so let's do an equation here. I'm going to get this stuff out of the way now. Y equals mx plus b. We have our m, we have our b. Oh, lost my y. And we'll get y equals 1.2 x plus 2.3. So we start at 2.3, and this should make sense. When x is 0, when there's 0 time passed, when your puppy was born at 0 weeks old, 1.2 times 0 is 0. She's born at 2.3 pounds. As x goes up the number of weeks, you end up saying, oh, okay, we're going to add however many weeks, whatever, with that rate to get the pounds. Okay, part B, I'm going to do it over here. How long until she weighs 70 pounds? So this is important here. You see that 70 and that pounds. Pounds represents y, so we know that we're going to substitute 70 for y. 70 equals 1.2x plus 2.3. Another way to recognize that, it says how long? How many weeks? All right, that's what we're trying to figure out. So we're trying to figure out x here. So we solve for x. Subtract 2.3, and you know what? I don't have my calculator with me, so I'm going to look at this answer sheet here as I go along when I do this division. Okay, so you subtract. We get minus 2.3. We got 1.2x equals 67.7, I believe. And when you divide that, let's see what they did. X equals 56.42 weeks. That's about like 50. So 50. You know, if there are 52 weeks in a year, so it's about a year and a month, another 4 weeks, a month, and then that Wednesday. You know what I mean? Like on our number at 6 a.m. Right? So your puppy's gonna gain 70 pounds. Now that's a fat pup, I think. I don't know how fat that is, man. I don't have a puppy. But, right, so that's the idea behind that. So you do that problem. Okay, explain the limitations of this equation. So here's the thing. I'm going to do a really, graph of this. There's my x and y. Now this graph looks kind of like it crosses at 2.3, right? That's my y-intercept, and it goes up 1 over 1. Let's just say it did that. And here's my time scale. My x is weeks, time passed, and this is pounds. So we know at 0 weeks old it does that. We also know at 56 weeks old right here. So let's say here's like 60. At 56 weeks old, I'll do a little less. Here's 60. We know that this is 70 pounds. All right, well, here's the thing. Weeks go by. We even go to 120. All right, pounds is going up, man. This dog is getting fat. Right? This is a little more than 2 years after it's born. It gets huge. Go to 500 weeks. This thing's huge. It's huge, man. It's a beast. It fills up the classroom. There's a problem here with the linear equation, and that is, for one thing, you can't have negative weeks, so there's a bound right here. For another thing, this thing keeps going linearly. We don't grow like that. Yeah, for a while we grow at some rate, and it makes sense for a while, but after some time, man, we kind of plateau. We kind of stop and do that. Sometimes we lose weight. Nothing's predictable, but the fact is we got to stop at some point. Right? Dogs don't weigh 600 pounds and keep going as they keep getting older. So that's an important limitation here, and it won't grow forever. Okay, it stops at some point. So that's why linear equations don't always work for these things, and we'll talk about that when we do the scatterplot thing a little bit. Okay, here's another word problem. This was number 16, so it kind of jumped around. You're charging BHS to sit in the dunk tank. Awesome. You get dunked 2 times, you get paid $12. If you get dunked 5 times, if you get dunked 5 times, you get paid $21. Write an equation that models this and label your variables. All right. So this is where someone might get stuck. They're like, what? Thing is, we translate the word problem to a regular equation problem. We talked about domain and range a little bit as far as input and output. 2 times, 5 times, that's getting dunked. So that's an input. We dunk you. As a result, you get paid a certain amount. So input will be number of times dunked. And as you remember, if you go all the way back to the beginning of this thing, your input is your x. So I'm going to let my x be dunks. Like dunk tank dunks by number of times. Like total number of dunks. And your y represents dollars paid, money paid in dollars. Okay. Sorry, it shouldn't be money. It should be dollars. Actually, I think that represents dollars anyway, so that's okay. But, okay, it's important that I set up my variables. It does say label your variables. Super important to do that anyway. I can make much more sense of this problem now as I do this. Here's the thing. They gave us 2 points. You might not even recognize it, but they gave you 2 points. Here's a point, 212, right? 2, number of dunks, comma, 12, amount of money paid. 212, that's a point on your graph. Here's another one, 5, 21. X is 5, y is 21. So another way of putting this thing, once you get to that point, basically it says, write the equation of a line passing through these 2 points. Doesn't really matter what form you do, unless they tell you. I like to do slope-intercept form in the end, because then you're solving for y. But I'm going to use point-slope form to start and go into that, only because we haven't done that yet. Maybe it's a good help. So to do this, okay, I have 2 points. I need a slope. So what do? Slope formula. y2 minus y1 over x2 minus x1. 21 over 12 is 9. 5 over 2 is 3. Perfect slope. I like looking at this one. It's 3. But I'm going to write it a little bit differently. I'm going to write, oh, crap. I'm going to write this as 3 over 1. Because I want you to really know what this means. What did my y values represent? Money paid. So 3 is $3. It doesn't mean you get paid $3. It means you get paid $3 per every what? Number of times dunked. $3 per 1 dunk. Okay? All right, let's do this. So that's my slope. That's my m. So I'm going to do this in point slope form this time. I just want to shake this up a little bit. And I'm going to pick either one of these points. When in doubt, pick the smaller number of points. Might as well. Okay? I'll get y minus 12 equals 3 times x minus 2. Okay? I'm going to put this in slope-intercept form now. And to do this, you got to distribute and add your 12 over. So I'll keep the 12 over here for a second. Y minus 12 equals 3x minus 6. Add your 12. Y equals 3x plus 6. Okay, here's my equation. Now I want you to take a look at this one again and remember what x and y represented. X, let's bring this up. This will be important for the other equation anyway. X represented number of times you get dunked. Y represents money paid in total. So here's the thing. 3 is 3 over 1, $3 per dunk. If I get paid $3 per dunk, let's say I get dunked twice. Okay? You get paid $6 just for that. But, oh, by the way, you get paid another 6. So what does this 6 have to do with anything? Remember that fixed amount thing we were talking about? Okay. Remember when BHS kind of hired you to do this? You're charging BHS to sit in the dunk tank? Okay, BHS gets paid to do that, or whatever. So what that means here, let's plug in 0 for x. Okay. If I get 0 for x, I'll get 0 for this whole thing, so y will equal 6. So if x equals 0, if I don't get dunked, I will get paid $6. So what does that mean to you? What that means is no matter what, you're up front, you're getting paid $6. And then they say, oh, by the way, every time you get dunked, we'll pay you an extra 3. Okay, so that's all that 6 means right there. They want to pay you up front, and then plus the rate you get dunked. So if you don't get dunked at all, hey, you still walked out $6. Get an In-N-Out burger. Get some fries. All right, but okay, we have this equation. We're good to go. We labeled our variables. Here's part B. If you get paid $66, how many times will you get dunked? If you get paid $66, here's where the importance of looking at your variables really helps. Oh, money paid. I'm plugging in 66 for y. I know that because I have that written down. 66 equals 3x plus 6. Subtract 6, yada yada, solve for x. You'll get x equals 20. Now what does 20 mean? What that means, and I love for you to write sentences whenever you can. I'm not sure I did that for the other problem. Well, I know I didn't. I'm not sure if they asked me to. You will be paid $66 if you get dunked 20 times. It's very nice to write that sentence out. You make better sense of your problem with that. That's kind of why I like word problems. It's kind of a nice thing behind that. So you get that answer. You say, does it make sense? You know what? Yeah, it kind of does make sense. Excuse me. Okay, let's do some graphing. I don't want to do too much with this. I don't want you to get way over your head with it and make this run way too far over. Especially because these two don't even show up here. Every form has a little shortcut method to be able to create a graph with little or no calculation or tables involved. That's why they have these forms for you. They say, we can be graphable with these. You do little transformations to go from one to the next. I'm going to do something with them. We don't like standard form too much, but you can still graph with them just by 2 points. Remember, these are linear equations. I just need 2 points for them. What better than my x and y intercepts? Okay, by setting the other value equal to 0. By the way, my x-intercept is a point when y equals 0, and my y-intercept is a point when x equals 0. So what you'll do in standard form here is plug in 0 for y and solve your value for x. Plug in 0 for x, solve your value for y. Let me write an equation and make good sense of this, like 2x plus 3y equals negative 6. If I wanted to solve for my x-intercept, I set y equal to 0. Boom, y equals 0, 2x equals negative 6, x is negative 3. So one of my points on my graph would be negative 3, 0. That's my x-intercept. My y-intercept, solve when x equals 0. All right, 2 times 0 is 0. Whoops. 2 times 0 is 0. That's not working. You know what I mean. Hide that. 3y equals negative 6. Y equals negative 2. So another point is 0, comma, negative 2. You plot those points, you graph them, you're good to go. Any other questions, please ask me in class. Point slope form. You start from the point that you're given, then rise and run with the slope. So in point slope form, let's say I have like y minus 3 equals 1/2 times x plus 7. Okay, the point you have, the point is -7 comma -3. Remember, positive 3. Remember, this is x minus -7. That's where we have that, and that's y minus 3. That's where we have that. So you start from -7, 3, and then you go up 1 over 2, up 1 over 2, up 1 over 2. Or what you can do is multiply this, put it in slope-intercept form, and then graph it from the y-intercept, which is the next point here. I will do one of these in the next, on the next screen. So I'm going to kind of avoid what I talk about, but start from your y-intercept, up 1 over 2, etc. Do your rise and run. We've done a lot of those. Okay, absolute value. There's a vertex form that we've done, and I'm going to write that right here. I really want to do a video that's an entire thing, like another hour with absolute value in case you're totally lost on it. Here's what we're looking at. Y equals a times the absolute value of x minus h plus k. A lot of new letters here. A is kind of your slope. I also call it amplitude or stretch factor. I'm going to start using stretch factor a little bit more when we do parabolas. The good thing about this form is you get exposed to it now, and when we do parabolas, it's going to make a lot of sense. It really is. Just you can't confuse absolute values with quadratics. Okay, your h, keep in mind, this is x minus h, but that h and that k are the 2 points that you use for your vertex. This capital V out here represents vertex. Now notice, this is x minus h, so if I had x minus 2, my h would be 2, not -2. If this said x plus 2, my h would be -2, because x plus 2 is x minus a -2. So this is x minus h. So that's going to be something confusing for a while, but you know what? You do this right here already, right? Haven't you done that with x minus x1? So we've done that a little bit, just we haven't really extracted a point out from there. We put this into there. So there's your vertex. Your stretch factor is like your slope. So if this was 2, it would be up 2 over 1, up 2 over 1. Yada, yada. So graphing it, you start from your vertex, and then you rise over run in mirrored directions. I'll show you what that means when we do graphs, because we're going to have 5 of them. Now, each time we do these graphs, I'm going to make sure it's in this form. If it's not, I'm going to have to run it in this form. And there's one example, I think it's number 12, that's going to be a little bit different than the others. Oh, by the way, we'll be doing inequalities too. I'm not going to be talking too much about what you have to do with that. You'll do it here and you'll see it. Okay, numbers 10 through 15. Let me do number 15 first. This is a, it's not really in slope-intercept form right now. I'll move it into there and we'll make that one happen. Do the linear equation first, no absolute value. Let me rewrite this here. 2/7 x minus 5/7 y equals 10 over 7. Okay, I'm going to, you know what? I'm having trouble looking at fractions. I don't want to divide by 5/7. I'm going to multiply everything by 7 right now. Get those 7s out of the way. So I got 2x minus 5y equals 10. Subtract 2x. I got -5. Oh, you know what? You want to do it this way? You want to do standard form? Let's do standard form first and take a look at it. Here's another example of that. I'm going to solve for the x and y intercept. My x-intercept is when y equals 0. So if I plug in 0 for y, I'll get 2x equals 10. If 2x equals 10, then x equals 5. So one of my points is 5, 0. So I plug in 5, 0. Boom, one of my points. Same thing for y. Want to solve for the y-intercept? Plug in 0 for x. Why does that keep happening? I don't know. Anyway, hide that. Plug in 0 for x. We get -5y equals 10, so y equals -2. That should be -2. So one of my points is 0, comma, -2. I'll plug that in. 0, -2. Boom. So my graph, I just got to draw a straight line between these 2 points. Kind of easier said than done when you're looking at a, when you're using the smartboard technology here. So let's see. Okay, probably look a little bit like that. Draw your arrows, look nice with it, and there's my graph. I'll do it another way though. I'll put this in slope-intercept form from here. Subtract 2x equals -2x plus 10. Divide by -5, you get y equals 2/5 x minus 2. Okay, looking back at this other thing here, slope-intercept form, start from the y-intercept and then rise and run. So my y-intercept in slope-intercept form is my b. That's -2. Okay? I'll do this in red, actually. So for this form, I'm going to start at -2. All right? Right there, or 0, -2. Then I do what? Up 2 over 5 in the positive direction. Up 2 over 5. That point look familiar? I could do that again, kind of running out of space that way. How about this way? Down 2 over 5. Hey, that's a point we already drew. So that makes sense. We graphed it two different ways. Your choice on how you want to do it. Either way works. It's fine. Just draw the line and draw arrows as you do it. And remember, that was an equal sign. We'll run into inequalities and see how those look. Okay, I'm going back up from the top, doing absolute values now. Remember this form, y equals a times the absolute value. Absolute value of x minus h plus k. If it's not in that form, I'm going to put it in that form. By the way, my vertex is h comma k. Okay, number 10 looks to be in that form already. Y equals, what is my a here? My a is 1. 1 times x minus 3 minus 5. So what's important here is you got to know what this a is. A is 1. Your vertex is 3. Remember, it's x minus h, x minus 3, comma, plus k. This is a plus a -5, so that's 3 -5. So what I'm going to do is I'm going to start at my vertex. Okay, 3, 1, 2, 3, 4, 5, right there. And this is kind of your slope, but it's a mirrored slope. So because a is positive, that means these will go upward. And remember, it's a V shape, so I'm going to go up 1 over 1. Up 1 over 1, up 1 over 1, etc. The mirror about this, you can do this one of two ways. I'm just going to go up 1 over 1 this way. But the mirror thing about this, and this will be important when we do parabolas, is notice how I went up 1 over 1 here. I just got a mirror across here. There's this thing called an axis of symmetry that goes right down here. Basically means I'm going to create a mirror image when I do this. We'll do that a lot more with parabolas. But that's the idea behind this mirror concept. Let's see, I can do an arrow immediately here. Do this. And and you follow along that line. Boom, we did a graph. We didn't have to do any tables. I'm going to save you the pain from doing tables right now. There's our graph. Y equals x, absolute value of x minus 3 minus 5. Okay, number 11. Now this is a less than sign, so I'm going to work with that after I'm going to treat this as an equals first. You probably already see your answer key, so you know what it looks like. This is already in vertex form of an absolute value. Let's check this out. Negative in front means a -1. So my a is -1. My vertex, this is x plus 2, and I don't see a plus k out there. What that means is my plus k is plus 0. So x plus 2 means x minus -2. So my vertex is at the point -2, 0. So I'm going to start at -2, 0 right there. And then what? Well, my a is negative this time, and negative means I'll go downwards. And this is still a slope concept, so just like this one was 1, this is down 1 over 1. Down 1 over 1, etc. Go that way, and that way. Down 1 over 1, down 1 over 1. It's also a V shape because it's an absolute value. And I get to graph it. Woohoo! This way, drew my arrows. It goes on forever. Okay, number 12. This one's kind of an iffy one. Or this one's a little tricky. I'm actually going to do this down below first, then rewrite the equation, then come back up. Okay, this says y equals absolute value of 3x plus 6 minus 1. And I'm going to ask you if it's in this form. The answer is no, it's not. In this form, I can't have a coefficient in front of x other than 1. This has a coefficient of 3. I need to get rid of that. So what I'm going to do down here, I'm going to copy this. Y equals absolute value of 3x plus 6 minus 1. What I need to do is write it in that form, and in doing so, I need to get this 3 kind of out of the way. So I'm going to factor out a 3. And I can't factor it out of the absolute value, at least not yet. You need to know what you're doing first when you do this. So I'm going to factor out the 3 on the inside. Here I'll get x plus 2. This is minus 1. Now there's a property. And what the property is if you have an absolute value with a product inside, that's the same as the product of two absolute values. If I have a times b inside the absolute values, I can separate those into two different absolute values as long as I'm still multiplying them. Inside here I have a product, 3, treat that as my a, and x plus 2. Treat that as my b. So I can actually separate those. I can say y equals the absolute value of a times the absolute value of b minus 1. What's the advantage of that? Well, I've pulled out my 3 from this absolute value, and I can take the absolute value of 3, which is 3. I'm simplifying this just a little bit. Y equals 3 times the absolute value of x plus 2 minus 1. So this is actually now in vertex form, and you'll see that there's a difference between those. You'll say, well, there's still a 3. That's still my slope. Yeah, that's true. But your vertex is now different. In fact, this wasn't a vertex before. This was 3 times your vertex. Really, what we're trying to figure out is what value of x makes this inside 0. So what I'm going to do is I'm going to rewrite this equation. I don't like this one anymore. It doesn't help me. I want y equals absolute value. Oh, I'm sorry. Y equals... do a different color. Y equals 3 times the absolute value of x plus 2 minus 1. Okay, same thing as before. A is 3, positive 3, and your vertex is negative 2, comma, negative 1. Okay, let's get used to this pattern here. So start at your vertex, and we'll go our slope up 3 over 1, up 3 over 1, yada yada. Same thing. I mirror this across here. I mirror this across here. And I graph it. I don't know what color it was. Probably this one. All right. There's my graph. Looks beautiful, by the way. I love it. So there it is. There's that one. Any questions? Again, please ask away as needed. Oh, you know what? We're not done, though. So, I'm sorry. We are done. I want to go back to this problem again. I'm sorry. We did that equals thing. I got to look at it one more time. That's the problem with, you know what? That was a careless mistake that I made. This said y is less than. So how do we do that? I'm going back. This is all my b. All my b. How do we do that? Less than. I'm going to save you the time a little bit. Less than means below. It means what y value can I plug in below the y value that I'm currently looking at on my graph? Okay, so let me delete these for a second. I'm looking at a couple points here, and I've plotted these points. These points represent the absolute value of x plus 2. I'm sorry, negative the absolute value of x plus 2. I need y values that are less than that make this true. So if I plug in a point, say this point right here, negative 2, negative 5, this would make this true. Negative 5 equals, or is less than, whatever this is. Take my word for it, it will be. So what's going to happen here? The less than, it's not less than or equal to, it's less than. The less than indicates that anything on this broken line that I'm going to draw is not including points that'll work on here. Like if I pick the point negative 1, I'm going to get negative 1 is less than negative 1, and that's not true. Negative 1 is not less than negative 1. So this dotted line represents that. It says these ones on the line don't make this inequality true when I plug in those points. But when I plug in any point that's below, anything down here within this realm, that will make these true. So that's what you're aiming for there. You want something less than, that's going to, any of these points will make this thing work. Meanwhile, this wasn't equal to, any points that I plug in on this line will make this equation work. This is an inequality, this is an equation. Keep in mind, make sure I do inequalities for these next two. I'm going to delete some stuff down here. I need to transform this one. Okay, delete, delete. Number 13. Y minus 2 is greater than or equal to absolute value of x minus 1 plus 1. I'm not quite in the form, but I'm close to it. I kind of just need to solve for y. Add 2 to both sides. Y is greater than or equal to, can't forget that, absolute value of x minus 1. When I add 2, this will be plus 3. So here's my equation. What is a? Well, remember a is in front. That's a 1 out there. Can't see it, but that's 1 times that. So a is 1. And my vertex is 1, comma 3. So what I'm going to do is start from 1, 3. I'm going to go up 1 over 1, yada, yada. I now have to be careful with that. What was it, 1, 3? All right, start at 1, 3. 1, 1, 2, 3. I'm going to go up 1 over 1, up 1 over 1. Bippity boppity boo. Same thing on that side. We golden. Now we're not done. We still have to draw the lines, and I still have to make sure that I shade this, because this is an inequality. Now, why am I drawing these solid? Well, because it's also equal to. Remember, I plug in a point, like this one right here, I'm going to get 0 equals 0, Just take my word for it. Well, actually, will it be? No, it won't be 0 equals 0. Anyway, I'm going to get something where something equals the same thing. And that's true. Like if it was 3 is greater than or equal to 3, that's true. 3 is greater than or equal to 3 because it's equal to it. So these lines are solid when it's equal to as well, but I also need to shade greater than. And greater than is above. So let's go ahead and shade above this guy here. And you can test some points. I always recommend testing 0, 0, the origin. And in this case, if you test 0, 0, your statement should be false. I'll do it right here. Let's do one. 0 is greater than or equal to the absolute value of 0 minus 1 plus 3. So 0 is greater than or equal to absolute value of negative 1 is 1. 1 plus 3. Is 0 greater than or equal to 4? Of course not. 0 is not greater than or equal to 4. Therefore, this point, just like any other point that's below this blue graph right here, will not be true. So you test 0, 0. You say, do I get a true statement? If you do, you shade on that side. Make sure your math is correct. If you don't get a true statement, shade on the other side, like this one. Okay. Moving on over. Oh, you know what? This one was not absolute value. Oh, well. Inequality. Let's practice it right here. I'll do slope-intercept form. Might as well. Not going to waste too much time with the standard form. You can do it that way. But you got to be careful with this whole thing right here when you do stuff. And just whatever. Okay, let's do this. Add 4x. Negative 2y is less than 4x minus 10. Divide by negative 2. When you divide by a negative, your inequality flips. This is a crucial part right here. You got to flip that guy. Not going to spend time explaining it. Take my word for it for now. This inequality flips. This will be y is greater than negative 2x plus 5. So what I'm going to do when I graph this, I'm going to start at 5. 1, 2, 3, 4, 5. At 0, 5. And I'm going to go down 2 over 1, down 2 over 1, and graph that. Now, this is a greater than. So there are two things that's going to happen. First of all, this is going to be a broken line. Make sure it's blue. And let's make sure it's arrows and broken. So broken line because it's not also equal to, it's just greater than. Now greater than means shade above. I want to shade for y values that are above my other y values. So I'm going to shade above that way. Okay, so go ahead. Use green. Shade above. We're all good. That looks like a beautiful graph, and that represents everything that makes this work. If you don't trust me, test 0, 0, see what happens. Is 0 greater than 5? No. So 0, 0 doesn't work. That's why we're not shading on that side. Okay, we've done our 6 graphs. Took a while. We've done our 6th graph. Here we go. We're going to do one more thing here, and that's scatter plots and trend lines. Now, I'm doing this because you have this for tomorrow. This is something that's a part of your test tomorrow that you're going to do in groups of 3. Scatter plots are a way of predicting or estimating outcomes based on real-life data. So what you're going to do is you're going to have points. Maybe you surveyed something. Maybe you surveyed people's great GPA and hours slept or something like that. I don't know. We're going to do an example in a second. And you're going to plot those points. Now, not everything fits on a perfect line, so we're going to plot the points and find a line of best fit, meaning our lines best relate to something because it's something that's trending. Meaning if both things go up or whatever else, they seem to form a pattern. When you draw that line, you're going to try your best to place the line on at least 2 points. You can find a slope and y-intercept. I'll explain that as I do it. You're going to understand why there are limitations. We did that with the puppy and age, weeks in pounds and stuff like that. Excuse me, I want you to really understand limitations for linear equations. So let's go and do one. All right, the following graph gives data about information about the number of Starbucks stores nationwide. So here are the years you have, and here are the number of stores that they had as we went each year up. Now the important thing here is this is going to be your input and output. Treat that as x and y. When you input a year, this is the output that you have. The important thing here is I want you to understand I'm not necessarily going to do 2003, 2004, etc. I'll treat 2003 as a year, like, I can treat 2003 as year 0 if I want. Or 2003 as year 1, or as year 3. I don't want to go have this be year 0, like before Christ and whatever AD stands for. And here's 2003, 2004, 2005, etc. I want to get these a little closer and a little more scrunched up. In fact, I'm going to look at the answer key that I scanned for you guys and treat these as years 3, 4, 5, etc. So year 0 will be the year 2000. Year 1 will be the year 2001, etc. So I'm going to change these to 0, 1, 2, 3, 4, 5, 6, 7, 8. It's an important thing. You might have done that a couple times before in graphs. So I'm going to do that here. So when I do that, here's 1, 2, 3, 4, 5, 10. So here's this year 10 is really year 2010. Just something to keep your eye on when we do this problem. All right, now those aren't perfect, but you know what? You need it to be a little perfect if you can. The other thing here, you can kind of change this if you need to, and not too much. Remember, these are rough estimations. We're going to do as best as we can with this. I'm just going to do these by the thousands, right? If I do number of stores per 1,000, like times 1,000, I can change this to 7, 8, 10, 7.2, 8.5, all that. But these numbers are going to be rough estimates. This is about 12.4. This is about 15.0 and about 16.7. So I can change those numbers. Why? Because I don't want to write that much. I'm kind of lazy. You see that on your answer key, I think, as well. What I need to do is I need to create a cap. I'm going up to at most 20 for here, it looks like, because there's 16. So that means here's 10 right here, here's 15, and here's 5. Now, these are in the thousands. These are times 1,000. I want you to label your graph when you do this. X is referencing the year. X is in years from 2000. Y is the, what is that? Starbucks locations? Starbucks stores per every 1,000. So what we're going to do now is plot these points. Now I know you know how to plot points. Let's see. We got 3, 7.2. See, it's easier for me to see this anyway. And about 7.2 right there. Good enough for me. We'll do a rough estimate. It's going to show a trend. That's the point, though. 4, 8.5. Yeah. 5, 10.2. A little more than 10. Not too much more. 6, 12.4. So that's really close to right in between. 12.5 is right in between 10 and 15. So it's right there. 7, 15.0. So I'm going to put it right there. And 8, 16.7. So it's a little more than 15. Okay. All right. Graph the data. Clearly label your axis. Draw a line of best fit. So we've done that one and that one. Draw a line of best fit. Here's the thing. We look at these points. Oh, you know what? I might have skipped some stuff. Yep. My bad. My B. Let's do part A. From looking at the data, what can you conclude about the number of stores? So this was before we graphed. Again, my B. We're going to look at this stuff, and we'll say, okay, as the years increase, as we go every year, we're increasing the number of stores. That's just looking at it. You can see these numbers here, 7, 8, 10, 12, 15, 16. Those are in the thousands. So I'm going to type here. When as the years go by, so as we increase the number of years, the number of stores increase. I'm seeing that pattern. I don't know by how much, but I know it keeps going up, and it seems to be a nice pattern. We're going to determine whether it's linear. Assuming this relationship is linear, what can you conclude about the slope? So the thing is, we know that the number of stores increase as the years increase. So we can assume that this slope here is going to be positive. So we know it's linear, which means we're talking about slope. So we're assuming positive slope. Now we graph the data, label our axes right here, and draw a line of best fit. All a line of best fit means is that you take a line, and I'm going to try and make it skinny. You take a line. I'll make it, let's do blue. And you're going to graph it through these points as best as you can. You're going to kind of rough it. So first I'm just going to I'll kind of get it through those things, kind of like that. And then I want to kind of finish it off and say, okay, I want to, okay, you know what, that's not that bad. I want my line to kind of look like that. What you want to do, though, when you do this, is you want to try and get your line to pass through at least 2 of your points. I'll explain why when we do these next. It says find a good representation. You want it to kind of pass through 2 points if you can bear it. But this line kind of represents these points. It's a nice fit. It doesn't exactly go on every line, but we're not squirming through. We're not going like that. I want this thing to be a predictor for what I'll do for the rest of my points. We'll look at this and say, all right, well, where are some limitations and all this other stuff? So it's going to make sense. So looking back, remember when I said try to place the line on at least 2 points you can find a slope and y-intercept? The reason is because you're going to choose 2 points that you already know. Now, in this case, we have rough estimates. I'm going to erase these completely, but I want to use these numbers exactly when I do this, just so I have something exact as I go about this. So these are in the thousands, keep that in mind. So one of my points really, the point isn't really, what was that? 7.2. The number really was 7225. So one of my numbers is 3, 7.225. Now my line goes through that point. That's important, because I'm going to use point slope form, slope intercept form to make this happen. This was 8, 16680. So what I'm going to do is I'm going to use those. And once it says find a good representation of the line, this means equation. Write an equation that you just drew. So I have 2 points, 3, 7725, and 8, 16680. I hope they use the same points. They did not. So my line is going to be different. I need to use a calculator to make this happen probably. So my slope is going to be y2 minus y1 over x2 minus x1. Okay. And so I have that there. I know 8 minus 3 is 5. I don't know this one off the top of my head as well. I know it's going to be, let's see, 9, 4, I hope this is right, 9455 over 5. That's a rough estimate. Okay, now I want to do this on a calculator. Calculator. See you later. You know what? I could have figured this out. 9455 divided by 5. 1891. So you know what's very nice about that number is it's not a decimal. Hey. 1891. I like that. That was, you know what? I was really lucky. I really was. I got some points that really worked for me there. And you know what? You look at the answer key and you're going to have a different number, but it should be pretty close. Right? It should be pretty close to this. In fact, I look at this, we get 1946.5. That's, you know what? That's within 50. That's not that bad. It really isn't. Because compared to this is in the thousands. Pretty good. Now, what does the slope mean? This is over 1. Remember that. 1891. That's 1891 stores per year. That's stores, not stones. Okay, that's what that slope means. We still need to find a y-intercept. We need to find out where this thing's crossing through in the year 2000. So what I'm going to do is plug in a point that I know, like this one. Remember I said pick the smaller point. Okay? Pick the smaller point. Plug that in. Let's do point slope form. You know what? Might as well. Let's have some fun with that. Y minus 7225 equals my slope, 1891, times x minus 3. I'm going to distribute, put it in that form, and do all that stuff. Then I'll add 7225 over. So I know I'm running over. This is for point D. This will be y minus 7225 equals 1891 times x minus whatever 1891 times 3 is. That would be, shouldn't have closed the calculator. 1891 times 3 will give me 5673. Okay, so that was 5673. Okay, add 7225 over. Now, you know, these are big numbers. This is y equals 1891x plus, I don't know that math either, negative 5673 plus 7225. 1552. Awesome. Not too bad in numbers there. 1552. Okay. That's my equation. Now I have to label these variables here. It's going to be important that we know what all this stuff means. X was years. Y was stores. M is my rate, how many stores I get per year. And 1552, I want you to think about what that means because they're not asking you here. If x is 0, that means we're in the year 2000. Remember, when I plug in 0 for x, year 2000. So when x is 0, that's 1891 times 0, which is 0. That means there were 1,552 stores in the year 2000. Is that respectable? I don't really know. That doesn't really sound right. I'm sure there were more. But that stuff we'll talk about in a second. So let me move this stuff over or up a little bit here. We see that this is all I need right now, the equation. Using your linear model, how many stores are there today? So today is the year 2014. Okay. Now the year 2014 in my book is 14 for x. So this is that important thing. It's going to be kind of difficult to make sure that you understand where your year 0 is and you don't screw that up. I think it'll make sense when you look at your number. Again, that's why I like word problems, that you would have like a way weird number when you do that. So it would be massive, and it wouldn't really fit your model. So 1891 times 14 plus 1552 is 28,026. So again, it's still a big number. It should be, by all accounts. What was it? 28,026. So what unit is that in? That's in stores. How many stores are there today? There are 28,026 stores today in the year 2014. That's my answer. Now, what did they? Whoops. Now, in the equation that I see in the answer key, it's 28,636 stores. So looks like I'm off a little bit more. Your slope's a little bit higher in that other one. It's going to change things as we go down the line. So obviously, you can tell line of best fit. You know what? You use your best eye, and I just drew that right in front of you right here. Could have I made this a little less steep? Yeah, absolutely. Could have I made my graph a lot better? Yeah, absolutely. Right. So these things are way, it's a rough estimate, man. That's why predictions are kind of iffy. But you know what? All things considered, 600 as a difference between 28,000 and 28,600, that's not that different, man. That's a lot of stores, though. According to your model, when will there be 40,000 stores? So that's for y. We'll do 40,000 equals 1891 times x plus 1552. Okay. Subtract 1552, so 1891x equals, let me try and do that in my head, 38,448, is that right? Shoot, I might as well do this, I don't want to screw up. 40,000 minus 1891. See, I was way out, whoops. 1891. 40,000 minus 1552. 38,448. Awesome. All right. So of that, divide now. X equals 1890 or 38,448 divided by 1891. Not even trying that in my head. 20.3. 20.3 years from now. So here's the thing, or not from now, from year 0. So here's how we're going to answer this. What's 20.3 years from year 0? That's the year 2020 and a couple months. So writing this answer here. Okay, there will be 40,000 stores in the year 2020. Is this a correct thing to say? Here's the thing you have to be careful of. It says, when will there be, and if we're using exact integers, there will not be, there will be in the year 2020, but by January 1st, 2020, there will not be 40,000 stores, there will be less. So I want you to keep in mind and make sure that you know within the year 2020, from January 1st to December 31st. These are the kinds of things, man, when you answer these questions, they're super important to answer wordy like that. If you're talking about people, you can't have 20.3 people, so you have to round down. You know what I mean? So there are certain things that you have to really make sure that you have. Okay, check your results online. Give your reasons why you're close or not close. What? I think it says check your results online. I don't know if they have that predictor stuff on here. Let's check the 2014 one. I'm going to go and Google this. I haven't done this yet. I have no idea how many there are. In fact, you can check out the answer key there. It says there are currently 23,188. How do you check online? Well, Google's your best friend. You know that. Let's see if I have wireless internet here. Number of Starbucks stores in the world. That's good enough. I'm sure Wikipedia has the answer. Starbucks! There are 23,305. So, look, whenever your teacher, which teacher did this, did the answer key, we gained 100 and I can't add. 117 stores since then. Look how many stores we gain. That kind of makes sense, right? Because we gain about 1,000, almost 2,000 a year, or however much based on that. That's kind of impressive to say that this number gained. I can refresh this page. I can probably refresh this page right now. Let's see if it changes. No. But I can refresh this page in 2 weeks, and you're going to see a different number. Because you keep building Starbucks, man. Starbucks is getting popular. Give your reasons why you're close or not close. So let's see if we were close or not. So we made the predictor. I made the predictor here. I said there'd be 28,226 stores. Prediction. Yeah, right. The real one is 23,305. You know what? That's not bad. That's kind of close. But the thing is, you have to remember this line. This says they're going to keep increasing by the same rate. You know what? To me, if you think about realistic, we think our line's just an approximation. I think we're going to over-approximate. I think eventually it's going to taper off and kind of do this and start to flatten out. That's what most things do. Now, why is that? Okay, I want you to think about that. Well, that Starbucks becomes less popular? No, it's because the world is a finite place. And there's so many Starbucks that you can build. There's so much land that you have, where eventually you'll have 2 Starbucks across from each other like gas stations. And it's, there's not enough popularity to have Starbucks like that. You need to make sure that, eventually it tapers off. There will be so many Starbucks that they stop building them. They keep building them, but they don't really keep building them, right? This rate does not keep going. But you know what? This isn't bad. Really, that's not bad. But as this keeps going, I think in the year 2020, I think it's unrealistic to say that there will be 40,000 stores. I think you're going to be looking somewhere in the 30,000s, 35,000, something like that. Or less, actually. So in 6 years, we'll go back and look at this video. Okay, that's all I had for you. That was the practice test and all that other stuff. I do want to talk about domain and range with absolute values, but I want to do that in another video. Hopefully I can get that. And hopefully this was very nice. This was running me over an hour, probably closer to 2 hours. So I want you to watch this video, and hopefully you watched the video as you went, but I want you to jump to the things that you don't know as well, and then use that. But this was a study guide for y'all. I really hope it helped, guys. If you have any questions, please ask through School Loop. I'm going to post this. When you watch this, it'll be posted. So this will be posted. Ask questions in that lesson. Okay? So good luck to y'all during this test. Hopefully this stuff makes sense, and see you later.